This is lesson 1 of unit 11. In this unit, we will study gases. Gases is a very important part of the world around us, and studying gases in chemistry will allow us to see into many features of the world and many features of the chemicals, since every chemical can be made into a gas. So a very important area of study in chemistry. We'll begin by defining temperature and pressure. So the first definition we'll give is the temperature. Have you ever thought about what does it mean if you have a thermometer? What does it mean that the temperature on the thermometer is 25 degrees? What is that measuring? Well, it measures the average kinetic energy of molecules, roughly. And the idea here is, here's a box that depicts a bunch of little particles, little gas particles flying around. If you were to increase the temperature, make the temperature hotter, say if you put a Bunsen burner beneath here, what will happen is the particles will heat up, and that will be registered on the thermometer, but the particles will start moving faster. And that's really what the idea here is. The particles will start going around faster because their kinetic energy has been increased. Now we do the average kinetic energy, not the energy of a specific molecule, but the average speed of all the molecules. Just like in a class, we would take the average of the entire class, not the average of it in each individual student. And it's kind of difficult to measure the average of, or to measure the velocity of each individual particle. And there are billions upon billions of particles, so we actually do it as a whole. We take the average of this. Now, kinetic energy has an equation associated with it. If you took physics, you probably would have seen this equation. And this idea of kinetic energy applies in physics to big objects like basketballs. We're going to apply it to tiny little objects like atoms. And the equation is this. Kinetic energy equals 1/2 mv squared, where m is the mass, in kilograms usually, and v is the velocity. And so there are two parts to determining the energy of a particle, their mass and their velocity. And we'll explore this idea with the following few questions. The questions are, what is the difference between helium atoms in a 20 degrees Celsius bottle and a 100 degrees Celsius bottle? So we have two bottles here. Here's one, and here's another. And we have helium atoms. This one is at 20 degrees C. This one is at 100 degrees C, quite a bit hotter. What would you see about the atoms? Well, you would see, since this one has a higher, this one has a lower temperature than this one has a lower kinetic energy than this one, which means the particles would be traveling faster in the 100 degrees Celsius bottle, and they would be traveling slower in the 20 degrees Celsius bottle. So we can draw it like this. And because the kinetic energy is directly related to how fast they go. How about the second question? Which gas particles are moving faster, argon atoms at 25 degrees Celsius or helium atoms at 25 degrees Celsius? So here we have two bottles, same color. Here we have two bottles. And in the left bottle, we have argon atoms at 25 Celsius. Here we have helium atoms at 25 degrees Celsius. Now, the argon atoms are heavier, and because they're heavier, they travel slower. Both of them have the same kinetic energy. So if you take a look at the kinetic energy equation, kinetic energy is 1/2 mv squared. Since the argon atoms have a higher mass, since this number is higher, its velocity must be lower for it to still have the same kinetic energy as a helium atom. This is the same concept that says a car has less energy than a big bus, even though they both travel at the same speed. That's kind of the idea. The argon atoms are actually quite a bit bigger in terms of mass. So let's think about them being bigger. So they're slower. So let's actually draw the argon atoms moving slower. And the helium atoms are smaller. And let's draw them moving faster. That's the idea. So argon atoms, because the answer is argon, because heavier, more massive particles. And that's how you apply the kinetic energy equation to our idea of gases. Okay, take a look at the next slide, which lists the units of temperature that are commonly used. The Fahrenheit, degrees Fahrenheit, are used almost exclusively in the United States. Europe uses degrees Celsius. The rest of the world uses degrees Celsius essentially. And degrees Celsius is also called centigrade. Now the reason why we call it centigrade, also called Celsius, is because the prefix centi means 100, and the freezing point of water is 0 degrees Celsius. The boiling point of water is 100 degrees Celsius. And what we've done is we've made essentially 100 marks between those 2 points and called each mark a Celsius or a centigrade. That's why both of these are actually equivalent, Celsius. Now, chemists actually use the Kelvin scale. The reason why we use the Kelvin scale is because, as you'll see in a minute, it does not have any negative numbers. No negatives. No negative numbers. And this is very important for chemists. Fahrenheit, by the way, is also used in places like Palau and Guam. So if you don't know about them, you're in good company. No, not many people do. Okay, so let's take a quick look at this slide that has the 3 temperature scales essentially compared. And if you take a look, the Celsius and the Fahrenheit scale, you may know about this point here. This is the freezing point of water. Freezing point of water. Water freezes at 0 degrees Celsius. On the Fahrenheit scale, it's 32. On the Kelvin scale, it's 273. And this number is very special, 273. We'll see it in the next slide here, in the next few slides. At the very top, we have the boiling point of water. This is the boiling point of water. And what water boils at 100 degrees Celsius, and at 212 on the Fahrenheit scale, 373. So if you take a look, the scale is actually scaled the same way on the Celsius and on the Kelvin scale. In other words, from 273 to 373, that's 100 degrees. From 0 to 100, that's 100 degrees. In fact, this increase is the same as this increase. There's 10 increase here, 10 increase here. But the Fahrenheit scale does not increase by 10. It actually increases, if you take a look, by 18. So a Fahrenheit degree is not equal to a Celsius degree, as you'll see. By the way, this number right here is a special portion to it. This is where the Celsius...
A reminder, the lasagna is ready in the comments, so come on down.
Thank
you.
I love lasagna. Time for some lasagna. Okay, we're back. And what we were saying is that the Celsius and the Fahrenheit scales actually meet at negative 240 degrees Celsius and negative 240 degrees Fahrenheit. The Kelvin scale will never meet, is the idea. So here on the next slide are a few example problems. Or actually not example, a few equations. These are the equations to convert between, and then we'll do a few example problems. Converting between Fahrenheit and Celsius. So if you want to solve for Celsius from Fahrenheit, you would take Fahrenheit, subtract 32, and then multiply by 5 nines. Now 5 nines, this number right here, is actually the conversion factor between Celsius and Fahrenheit. You also see it here, except it's backwards because you're going from Celsius to Fahrenheit. 9 degrees Fahrenheit actually equal 5 degrees Celsius. This here is a conversion factor. The plus 32 and the minus 32, this is how far the distance is between 0 Celsius and Fahrenheit, essentially. So this is distance from 0, distance between degree C and degree Fahrenheit. Really, you don't have to understand the details of these equations. You have to just be able to use them. In fact, we're going to use them in just a minute. Now, before we can do that, let's connect this to the Kelvin scale, and we'll do it with these questions. How high can temperature go? Is there an upper limit? Like, can you get 5,000 degrees centigrade? Can you get 5 million degrees Fahrenheit? It turns out, yes, no limit. There is no limit to how high you can go. The second question is, how low can temperature get? Is there a lower limit? And yes, there is a lower limit. The reason is, when you reduce the temperature, the particles slow down. begin with a higher temperature, then particles slow down, and then eventually the particles slow down and it'll stop. And you can't go any slower than stopped, and that would be the lowest possible temperature for molecules. So there is a lower limit, and this lower limit is actually called absolute zero. The lowest possible temperature where molecules stop moving. It occurs at negative 273 degrees Celsius. So this is how much colder from the freezing point of water absolute zero is. And this is equal to 0 Kelvin. So the Kelvin scale was set up to be 0, the coldest temperature to be 0, and then everything warmer would be above. So the Kelvin scale has no negative numbers. And that's partly why it's called the absolute zero. It's the only absolute scale. There are no negative numbers. To convert between Celsius and Kelvin are these two equations. To solve for Kelvin, you just add 273 to Celsius, because 0 Celsius is 273 Kelvin. And then to go the other way, you would subtract 273. So you can convert between these two. Let's go ahead and do an example problem. And the example problem asks us to convert 245 Kelvin to degrees Fahrenheit. So we have to go through Celsius. So Kelvin is connected to Fahrenheit through Celsius. So let's first convert to Celsius. So degrees Celsius would equal Kelvin minus 273. In this case, Kelvin is 245. And then we want to subtract 273 from 245. Go ahead and do this on your calculator or in your head. And you should see that the answer is 28, negative 28 degrees Celsius. And now, let's go ahead and convert to Fahrenheit. The equation to convert to Fahrenheit, if you take a look, is degrees Fahrenheit equals degrees Celsius times 9/5 plus 32. So you take your Celsius, negative 228, multiply it by 5 by 9/5, and then add 32 to it, and you should get yourself an answer. Go ahead and try this. This answer should be negative 18.4 degrees Fahrenheit. Negative 18 if we're using significant figures. So negative 18 degrees Fahrenheit. Okay, so go ahead and try an example on your own, this practice example. And this completes for us lesson 1 of Unit 11.